The Venturi effect is a specific example of Bernoulli's principle and is defined as the reduction in static pressure and increase in velocity as a fluid flows through a constriction. Atomically, the pressure differential is from particles colliding more frequently as the cross-sectional area decreases. It is this pressure differential that leads to the increase in velocity as particles rush to the lower pressure environment. The kinetic energy of the fluid increases when the velocity increases, so to maintain conservation of energy, the potential energy must decrease and is shown to decrease by the decrease in pressure.
Using what we learned from making a testing model, we decided to use an air mattress pump as the air supply because it offered a known constant flow rate that could be used for data. To represent the fluid particles, we found foam beads that are very light and move freely within the pump's airstream.
The video on the left shows a slow motion video of how the pressure differential shown in the manometer changes once the pump is switched on. The video on the right shows a slow motion video of the collisions of the pellets on the walls of the tube as it passes through the stricture. The three main equations used are hydrostatic pressure, the continuity equation, and Bernoulli's equation, all equations we learned in class. In order to determine the velocity of the fluid inside of the tube, we use the other two equations to solve for the pressure differential and the initial velocity. Solving for the pressure differential, we use the height difference from the manometer. To find the velocity inside the tube, we use the rated volumetric flow rate given along with the cross-sectional area. Finally, using those values, we are able to compute the velocity inside the tube using Bernoulli's equation. Based on the conservation of mass and the fact that the area of the stricture is 2 times smaller, the theoretical value inside the stricture should be 4 times that of the inlet velocity. With the initial velocity being 10.075 meters per second, the expected velocity should theoretically be 40.3 meters per second. With the actual velocity inside the tube being 38.23 meters per second, there are some clear sources of error that can be attributed to the difference. The assumptions listed are contributors to the difference in values. The last one, specifically shown in the picture, exhibits the curvature at the bottom of the manometer isn't exactly in the shape of a half circle. This would have made our measured height different, propagating that error to a pressure differential.
The Venturi effect has many applications, such as blood flowing through vessels, spray nozzles, and airplanes, all of which utilize this principle for different purposes.
There were a couple of limitations and some improvements we noticed while building and testing our system. We attempted to read the internal pressure with gauges, but the circulation of the system did not produce enough pressure buildup to be readable. Also, we think two improvements would have been having the ability to vary the pump speed and having a single piece Venturi rather than using glued sections.